Hi, everyone. This is the solution to question 4 on the homework set. We are given an assembly of strange objects stacked up on each other. So it looks like we have a horizontal bar CD, and it happens to be horizontal due to the length of the cable that's been drawn out here from this little electric winch that has been created. And if we were to adjust this, if we were to adjust the power, right, we could make this bar be inclined, or we could let it be declined, right, if we change the length of that cable. But in its current position, we've got that 50-degree angle, and we have two boxes sitting up on top of it. In this problem, we are asked to draw a free body diagram for beam 3 and solve for the horizontal reaction in D. So essentially, we're being asked to solve for D sub X. Okay, let's get to our free body diagram. And we're given some information here, right? So W1 is 50, W2 is 30, and the weight of bar 3 is negligible. So we're going to set that one equal to 0. Just means it's not big enough to take into account in our analysis. All right, I think we're ready to go. So we're going to start with our free body diagram. We want to isolate bar CD. So you know what, this one actually, I think I'm going to do deductive. Let's see how I do with this. Just as a different teaching technique. Okay, so in order to get down to my bar CD, the first thing I'm going to do is erase all of this. I definitely don't need instructions. And I'm going to come over here and I'm going to cut through the cable and get rid of all this nonsense. I do not want any of that in my free body. Clearly, I don't want anything. Okay. And since I have cut at that location, right, I do my little cut line here. And do my internal tension force. So I'm just going to call that T. It's probably the easiest thing to do. You could call it TBC if you wanted to do that, or keep it at that angle of inclination. All right. And now I need to get rid of these boxes piled on top. So I am just going to get rid of this stuff, replace it with its effect on the body. So all that stuff created a contact force. It has a point of application right there. And the contact force is a normal force, N. It's different than a body weight, W. And go ahead and sum that up. So 1 plus 2 is 80 pounds. So anything of that nature would get full marks on this. And the other thing that we have to do is we need to take out this bolt and totally disconnect this connection. Okay, so I'm going to get my eraser. So I'm going to remove the bolt. I'm going to take off this bracket. Let's get rid of all this, right? I'm definitely going to get rid of this plain GG. I don't want any of that in my free body. So we have to remove the connections and replace them with their effects on the body. And just to make that as clear as possible, right, I'm just going to recolor this yellow color. So we've just kind of taken that bar out of context, and the original connection was a pinned connection. And so I know that at D, I have the ability to develop reactions that are horizontal and vertical. Okay, and I'm going to label them, D, dx, and dy. And I can deduce their directions based on static equilibrium. So if I look at the summation of forces, I look at the summation of forces and the x direction is 0, I see a leftward component of that t, and so I'm going to need a rightward component here. And for d sub y, I'm trying to think based on where you're at in this course. Yeah, you can still do it. All right, so if we did a qualitative summation of moments about C, if I do summation of moments about C and set that equal to 0, then you've only got two forces in the system, 80 pounds and unknown d sub y. The 80 pounds tends to pivot the body clockwise, negative thumbs down. Therefore, d sub y needs to, for qualitative equilibrium, needs to pivot the body counterclockwise, positive thumbs up, and that's only going to happen when dy is upward. Okay, so we've got our reactions in the correct direction now, and we're ready to do our quantitative work. We're asked to find d sub x, and our quantitative procedure, like in many problems, follows and syncs up with our qualitative procedure pretty well. So let's do a summation of moments about C, set that equal to 0, and that's going to allow us to solve d sub y. After we know what d sub y is, we can solve for t, and that'll let us solve back for d sub x. So a couple steps on this particular problem. For that tension force, as I am prone to do, I will break it into its components. So something like this. And have our t sub y and our t sub x. And we can use that 50 degrees. So t sub x is going to be cosine 50 degrees times t. T sub y is going to be the sine of 50 degrees. Multiply that by t. And when we're expressing the vectors that way, then we're no longer paying attention to the resultant. We're just substituting it with the components, one of those equivalent systems that we learned about. Get that out of there. Okay. If we're summing moments about C, then if the resultant force T is coincident with C, then the components also cannot produce a moment about that point. So I'm going to have two terms in my moment summation. And so my first term, 80 pounds, that's at a distance, and I covered it up, but it's at 2 feet, from here to here. Then there's another 2 feet over here. So the 80 pounds has a moment arm of 2 feet from C. That one is negative clockwise. Next term, d sub y, it has a moment arm or distance of 4 feet from C, and its tendency to rotate is counterclockwise, positive thumbs up, and d sub x is coincident, so that one doesn't create a moment, and we set all that equal to 0. D sub y is going to be equal to 40 pounds. And we got a positive sign, and so that validates our assumption that it is an upward force. We also could have used the lever law for this. If we wanted to use the lever law, I'm going to put this on top. So we could have drawn this free body like this. So 80 pounds here. And then over at the left, instead of having that tension force cut, I could have just taken the bolt out right and done like this push force here, that would be okay. And then I've got my two components, this one and this one. And then I've got this one and this one. And so I have these 1, 2, 3 parallel forces. They are spaced equidistant. So I'm going to get 40 up here and I'm going to get 40 up here. So you could have used a shortcut on that if you'd wanted to do so. At this point, we just need to figure out the horizontal component, d sub x. So I will go to another equation for that. And I'll write out the summation of forces in the x direction equals 0. D sub x has to be equal and opposite to tx, which is equal to cosine 50 degrees times t. We know that d sub y is equal to t sub y due to force equilibrium in the y direction. So from that, I can write that t sub y equals 40 pounds equals sine 50 degrees times t. And so we can say that t is equal to 40 pounds divided by the sine of 50 degrees. And I'm going to grab that expression and plug it in here to wrap up the end of my problem. D sub x equals cosine 50 degrees times 40 pounds divided by the sine of 50 degrees. And we remember, we can punch it into our calculator like that if you want to do so, but we remember the tangent identity. So if I've got my unit circle, so this is 1, this is theta, right? This is my cosine theta, this is my sine theta, and my tangent theta is opposite over adjacent, sine theta over cosine theta. So sine over cosine is tangent. So if I wanted to do one fewer calculator operation, I could do a tangent of 50 degrees down here. Okay, let me pull up that calculator wherever it is hiding. So 4t divided by tangent of 50 equals, and I'm going to get 33.6 to 3 sig figs, 33.6 pounds. That's my final answer for d sub x, and as shown in the picture, it has to be a rightward force for static equilibrium. Thanks for tuning in.